Okay. Hello. Here I am, always in the middle of the night. Not really, it's 10. Recording this video right before I have to give it to you. I love that. So, I took this review from a different teacher, so there's parts of it that, I might need to pause or rethink how to teach it. But I think I have most of the questions down, and they're not exact like the ones on the test, which I'm hoping you get to take on Wednesday and Thursday because I'm not here Friday. So let's hope this does a good enough review. The main idea of this test is dilations, and then there's gonna be a few questions on geometric mean like this. This specific review doesn't really highlight problems like this, so you're going to have to use the practice we've been doing in class, which is why it's one of the last things I taught because it's fresh in your mind. Okay, also I got Invisalign today, so I kind of have a lisp, and it's kind of embarrassing, so don't judge me, please, and if you do, keep it to yourself. Okay, so we have number 1, we have a line segment, and we're dilating it. Remember, dilate means to make bigger or to make smaller. There's 2 things we need. We first need to know where our center is, which it says at the origin, which is right here. All right, that's at 0, 0. Oh. And then our scale factor is 1/3. That's like 1 over 3. Which, if you remember, if it's a fraction, that means it's getting smaller. So this big line segment is going to get really small, and we're going to find out where. So I'm going to show you how to find that. Hopefully you kind of remember this once I get started with it. So first you take the center, like this is the center, and you find the distance from the center to the point on the line segment. So we're going to start with this point. So from here to here, we went 6 up and 3 across. I can really hear my lisp, and it's bothering me so much. Okay, so that's that distance. Remember, we're doing 1/3. So we have to figure out what's 1/3 of 6. If you don't want to do the math in your head, all you do is 6 times 1/3. So you take whatever that distance is and multiply it by the scale factor. Like this is the same scale factor. 6 is the distance. So 6 times 1/3 is 2. Or maybe you already knew that was 2. I don't know. So we're going to go up 2. And then the next distance we have is 3 right here. So we're going to do, okay, what's 3 times 1/3? And with that, you get 1. So then you go over 1, and your new point is right here at 1, 2. Okay, we have one more point to do. So I'm going to draw a line here. I think what we were doing in class was making triangles, if you guys remember, and then we would count the triangles. Oh my god, I literally cannot get this line straight. God, someone help me. Okay. So here's the triangle version of this. Maybe this will make it a little easier. Or not, because I can't draw a straight line for the life of me. Okay, can we pretend that that's like a straight line, maybe? I don't know. Okay, we're going to just pretend. Okay, so this right here, this length is 3. And this right here, if you count it, it should give you 9. So you can count like 1, 2, oh, like 1, 2, 3. You should count up and it should give you 9. Okay, then do the same thing. So 3 times 1/3 is, we already figured that one out. That's 1. So that was our vertical distance. So I guess we'll go up 1. Bro. Okay, up 1. And then 9 times 1/3 should give you 3. So 1, 2, 3. Giving us our point right here. I'm going to connect them too, because remember it started as a line segment, so we want it to end as a line segment. So our final line segment is right here. And if they ask for like the coordinates, you would write like, oh, you can't see, but this is 3, 1 for this point. And 1, oh, wow, 1, 2 for this point. So those are our new points. Yay. Number 2 is very similar, except this time it's a little different. Where we got a center at P, not like the origin. And our scale factor is 2. Since it's not a fraction, that means getting bigger by a scale factor of 2, which is like doubling, right? So whatever this line segment is going to get twice as big. So the first thing you want to do is draw that line. And then find your distance. I did 1 over and 2 up. And then I think this is where the triangles were making a lot more sense, I guess. Because then we had 1 triangle, but we needed 2 because, you know, scale factor is 2. So we'd go 1 over 2 up, giving us another triangle right here. Which gives us a point here, and this would be our A prime. P to B is interesting because it's just a horizontal difference. Like from here to here, there's no triangle. So 1, 2, 3, and I'm just gonna go 3 more, giving us a point right here. So like I kind of like doubled this. So this is the original, this is the second part of it. So this is B prime. And then you do a little connect moment because, you know, it's a line segment. And that's it. There's no coordinates like we had last time for this one because there's no numbers down here. Okay. Woo. Number 3. Let me zoom in on this one. It's a little weird. So it says, sketch a dilation of the lines centered at -3, -2 with a scale factor 1/2. That's a lot of words. Remember important ones. Center is at -3, -2. Okay, so -3, -2. That's right here. Cool. That's our center. Okay, our scale factor is 1/2, which means it's getting smaller. However, the thing about this is like weird because these aren't line segments, these are lines, which means they go on forever and ever. So I'm going to start with the easy one first, which is our red line. On your paper, obviously it doesn't look red because school does not give us color printing like that, but that's this line right here. And one reason I say that's the easiest is because if you remember with the shape, right, if you're dilating from a point on the shape or on the line, so this point is on our red line, then you don't have to do anything. It's before and after, it's in the same place, especially with a line because lines go on forever. So the red line stays so where it is. The blue line, however, you do have to do the distance thing and kind of treat it like a line segment. So I'm going to find 2 points on my blue line that I can like do the triangles with this point. So let's do this point right here and this point right here. Those are like perfect points. So first we got to find the like original distance from here to here. So we go up 1, 2, 3, 4, 5, across 3. Okay. I don't like this one. Is that supposed to be a perfect line? You know what? Scratch that. Ha 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 ha. And if I edited it, you guys wouldn't even be able to see that, but I'm not that advanced. We're going to use this as the line. Okay, trying again. 1, 2, 3, 4, 5, 6. There we go. 1, 2. Okay. So remember, half means we're cutting it in half. So half of 6 is 3, hopefully. You're thinking that in your head. Oh yeah, half of 6 is 3. So you go 1, 2, 3. Half of 2 is 1. So you go 1. So this is where one of our line points are. Let's find another one. I already did this right here. I'll see that. So 1, 2, 3, 4, 5, 6. 1, 2. Or it's literally the same exact things. Half of 6 is 3. Half of 2 is 1. And then you are going to connect those points, but since this time it's a line, it's going to keep going forever and ever and ever, which means you put arrows at the end and you extend it, right? With a line segment, you don't extend it, you stop at the points. With a line, it goes forever and ever and ever. Okay, numero 4. So with this one, hopefully not horrible. Again, it's all very similar, because like I think as long as you can do a line segment or like a point, they're all the same thing. It's just about doing it to multiple points. So this shape has 4 dots, so we're gonna have to do it 4 different times. Our center is B, which is right here. Scale factor is 3. Cool. So that means 1. Okay, sorry. I just started doing things without talking. Our center is B. Scale factor is 3. So it's going to be 3 times as big. It's getting bigger, right? It's not a fraction. It's getting bigger because it's greater than 1. Cool. So this tiny little rectangle is going to be huge. And that means the distance from B to all the other points is going to have to increase by 3. B will stay the same because since it's on the shape, dilating that point will not go anywhere. Like, it's just, you gotta stay at B. But the distance from B to C, or B to D, and B to A, that's gonna increase. So B to C is just 2 up, right? So we're gonna do that 2 more times. So we're gonna go 1, 2, 1, 2, for a total of 3 times. So this is our new C prime. From B to A is 1, 2, 3. We're gonna do that 2 more times. 1, 2, 3. 1, 2, 3. There we go. That's our A prime. Lastly, B to D. This one's diagonal, so we can say we go up 2 over 3. Do that 2 more times. Up 2 over 3. Up 2 over 3. That becomes our D prime. Connect it all. There you go. 3 times as big. Tiny rectangle became 3 times as big. Okay, that's the front side. All dilations. I know it's been a minute since we've done it because, so many days off and delays and all that. But hopefully that was a good refresher crash course. The back is where we're going to use... We're going to use our brain muscles a little more. For number 5, it talks about these different types of triangles and shapes we haven't really talked about yet, right? Like, I haven't told you what a scalene or isosceles is, right? Equilateral. Let me break that down for you just really quickly. So, scalene and isosceles triangles. Actually, let me break it down like this. So, we need shapes to be similar, right? Similar means not the same. It's not congruent. Similar means it's the same shape, so they're both gonna be triangles, just one slightly bigger than the other. They're proportional. That means the sides can be different, but the angles will always be the same, okay? Like, that's very important to remember. The sides can be different, angles can be the same, which maybe if you want to write a note to yourself, so when you're studying, you can be like, similar angles same, sides proportional. With scaling and isosceles triangles, so A and B, scaling and isosceles triangles always have different angles. Like, their angles are not all going to be the same. So what I want you to do is just cross those out, because those are not going to be similar with the before and after shape. Like, if you dilate a scaling triangle, it's not going to be similar. It's not always going to be similar. With an equilateral triangle, the sides are the exact same and the angles are always the exact same. That is just like a fact, because everything is equal. So by design, by default, equilateral triangles will always be similar. Like, no matter what, they will always be similar. I mean, yeah, they will also always be congruent. But in congruency, the angles are the same, the sides are the same. That means that they're proportional too. It's a 1-to-1 proportion. The scale factor would be 1, but they're still similar. Rhombuses, and I'm pretty sure it's rhombi, but whatever. Rhombuses and rectangles, however, always have a chance for, hold on, I'm reading just to make sure I'm saying this correctly. So you can have rhombuses that are not the same shape because the opposite angles are congruent. So with rectangles and rhombuses, not everything about them is always the same. Like, if you have two rectangles, there's things that can be wildly different about both of them. That does not automatically make them proportional. But if I have any two squares next to each other, you know that in a square, all the angles are 90, right? Like, in a square, no matter what, to be a square, all the angles have to be 90, because you have 90, 90, 90, 90. So all the angles are the same, even if you had small square and big square, right? That doesn't change. And also the sides are all the same. So by default, again, because everything's equal, they're not only congruent, but they're also similar. It's the same thing here for the equilateral. Like, these have the same exact logic. These are all, like, non-answers because of how wildly different two different rectangles have the possibility of being. There is a chance they can be similar. However, it's not always. When something is congruent always, like in a square or triangle, like, that's a fact. Like, those are always going to be 90 degrees on the inside and all the sides are the same. So it's always similar. The other ones are not. Hopefully that makes sense. This question specifically is on the test. I'm not 100% sure if the answers and stuff are the same options, but I really, really want you to remember, like, the squares and equilateral triangles for sure will always be similar, because if you have any two that are the same, you know, the facts are the facts. They always have to have that 90 degree. They always have to have the same exact side lengths. So by default, they're always similar. Okay, that was a lot of yapping about it. I'm sorry. I know that wasn't very easy to listen to, maybe. Sounded a little bit rambly. We're going to move on. Number 6, also a little bit of a yapper. I'm so sorry. So it says, given triangle ABC. I'm going to do some highlighting here. So ABC is the whole triangle. With angle, ACB is a right angle. So I'm going to draw that in. ACB. It's right here. Oh, it's already drawn in for you. You see that? Okay. So I'm just going to... CD. So CD's right here. Is perpendicular. Y'all remember that? Perpendicular. Hopefully you remember. Oh my god, perpendicular. 90 degrees. Right? I always said you want to relate perpendicular and 90 degrees together. Those are whenever I say perpendicular, you're automatically thinking 90 degrees. So CD and AB, which is this big line right here, are perpendicular. So again, we have 90 degrees. So I'm going to make two 90-degree angles right there. You're going to prove that ABC, the yellow triangle, so let's highlight this, yellow triangle, is similar, not congruent, similar to, okay, ACD, so that's ACD, and CBD. So that pink and green are similar to yellow. Okay. With this, we're going to bring it back a little bit. Y'all remember the little triangle congruence theorems of like ASA, SAS, SSS? I literally can't remember if I taught you guys AA. But that's just angle. If you have two angles that are the exact same between two triangles, then those triangles are similar. So we're going to use that theory. So first, let's talk about yellow. So ABC, triangle ABC is similar, that's my little similar symbol, to ACD. So that is our yellow to our pink. So the big yellow to the pink. Got it? Yeah. Oh my goodness gracious. Okay. First of all, with yellow and pink, we have the big... I'm going to actually erase this so that I can like narrate as I'm speaking. So here's the yellow. Okay, here's the pink. In both triangles, they both have a 90-degree angle, correct? Right, there's a 90-degree right here in that pink triangle, and in the yellow, there's a 90-degree right here. So they already have one angle that's the same. Cool. Remember, angle means we need two. So both have 90 degrees. Cool. That's one angle. I'm actually gonna write angle, and then I want you to add a check. Like, okay, we got one angle. Period. Next one. What's another angle they have in common? I'm gonna give you like 3 seconds of think time. Think. What other angle do ACD and AEBC have in common? Okay, hopefully you kind of heard me go A because they both have A, right? They both have angle A. So I'm going to come over here. All right, both have angle A. Boom. Angle, proven. So this first one, we got it. Bada bing, bada boom. Next one, it says ABC is similar to... Let me put a little check next to this one because we just did that. Okay. A. Congruent to CBD. Okay, so I'm going to erase this again so I can annotate for you to see it. So we have A, B, C. Right, that's our yellow. Cool. CBD, I literally can't remember what color we gave that, so I'm going to make it blue. CBD is right here. And that looks green. Whatever. Oh, I made another one blue earlier? Yikes. Whatever. With this one, again, they're both 90 degree. I mean, they both have 90 degrees because ABC, same place, right? Same place, it has 90 degree right there. But also, CBD has one right there. So, both have 90 degrees. Cool. So out of AA, right, we have 1A. Hopefully you get this one faster with A, B, C, right? A, B, C, C, B, D. What is an angle they also both have in common? Look at the letters. A, B, C, C, B, D. What's in common? Oh, I just realized there's 2 answers here. I love this. But the one I'm going to choose is B. They both also have C, but I'm going to choose B just to be different. So you can say both have angle B. That gives you your second angle, proving that they're similar through angle. I don't know if on your test it's going to be AA, but if it is not, it's literally written like angle. I think the full government name, similarity theorem. Okay. 2 more questions, guys. The last 2 are very similar, so once we do one, the other one should be like pretty easy. I do remember number 7, 8, like this type of question is your like written one. So lock in. Try to really understand. I'm going to try to explain it really well because it can be like weird without me having like my hand gestures as I am in class. Okay, so it says you want to project an image that is 10 centimeters wide, 6 centimeters tall on a wall that is 8 meters wide, 5 meters tall. What are the dimensions of the largest full picture that'll fit? I want you to imagine this like as if you're, you know, like those portable projectors that people watch a movie on. Like if you like buy one from like Amazon or something, you can watch it on like a blank wall. You know what I'm talking about? Hopefully you know what I'm talking about. So think about that. So you have like an image, like a small little square that is 6 centimeters tall, 10 cm wide. So it's like a little movie, right? Imagine it's a little movie, like your phone screen. And then you want to project onto a big wall that is 8 meters wide, 5 meters tall. So if you're not familiar, which I feel like I wasn't familiar until I was like in 10th or 11th grade at the very bare minimum, I think. Centimeters are smaller than meters. So since they're in different dimensions, you want to convert it so that they're all in the same one. So we're going to convert that meter into centimeters. The quickest conversion of that is you take like the number, so 8 meters, and there'd be like a decimal point here, right? 8 is the same as 8.0, and you would move it 2 spaces to the right. So 8 becomes 800, 5 becomes 500. So now it's 500 meters tall and 800 centimeters long. Hopefully that makes sense. Okay. Let me draw the big version of this. So then we have that, and it's 800. I mean, this is not to scale at all. We're pretending that's 800 centimeters. And there's going to be 500 centimeters. So as you're, like, doing this problem on the test, I want you to write that process of, like, going from 8 to 800, 5 to 500. Like, I want you to describe it. Otherwise, Like, it's not a full, complete answer. Okay. It's not the prettiest rectangle, but it'll work for now. Cool. So it's asking, if we were projecting this, what is, like, the biggest we can project it so that it still fits on the screen? Because you can project this image and have it still only, like, be, like, here instead of right here. But we want to make it as big as possible. So how do we do that? So the image that is 10 centimeters wide. Let's work on wide first. So 10 centimeters. We're going to see how many times does 10 centimeters fit into 800. How do you do that? You would take 800 and divide it by 10, because you want to see how many times can I take 10 into 800. So you get 80, which means you can make this picture 80 times as big, and at least width-wise, it's going to fit perfectly. So I'm going to take this long width of 10, and I'm going to make it 80 times as big in order to fit on this jumbo screen right here. Cool. However, you can't just make the width longer, right? Like, if you take a full image, like your phone screen, and you want to project it, you can't just, like, make it bigger long ways. You have to make the entire picture bigger. So now we have to worry about that 6 centimeters. Okay, well, let's figure it out. Is it going to fit in this 500 centimeters if we take 6 centimeters, multiply it by 80, right? Because we're making it 80 times as big. So 6 times 80 is 480. Okay. So we have an 800 centimeter wide, 480 centimeter tall. That's how big our biggest image can be. If we look here, 800 centimeters wide, it'll fit perfectly across. 480 centimeter tall, it'll come into, like, right here. Right here. But that still fits inside, right? Like, it'll be maybe a picture like that's right here. So it doesn't fit the whole wall. It doesn't go all the way up it. But it stops a little bit right before the top. So that is the biggest picture we can put onto the wall. That is the biggest size we can watch the movie from our phone to the wall. Hopefully that kind of makes sense. Your answer would be this. Okay. Number 8. Similarly, you are tiling a kitchen backsplash. You have to figure out how many tiles you need for the project, because your tiles come as one size. When you go to Home Depot and they give you a tile, like, they come as only one size. In this one, it's 10 centimeters by 10 centimeters. They're squares. So they're little square tiles. It's 10 by 10. Remember, all sides are the same for a square. Okay. And then your backsplash. That's, like, where are you putting the tiles? So in a kitchen, I don't know if you guys know what backsplash is. Like, you know, like when you have your counters on the kitchen and then there's, like, a little bit of wall before you have your cabinets. And, like, sometimes that wall is painted. Sometimes there's tiles on it. So a lot of people put, like, design tiles and make it look cute. I don't know. Let me see if I can actually find a picture. Because why not? Back splash kitchen. So like this. Like these tiles right here. Right, so we have the whole area, and in this, their tiles are rectangle, ours are going to be squares. You have to figure out how many of those squares are we putting on that background. In order to do that, you know, we got to do that conversion thing. It's the same thing. We have this small image, like we did here. We have this small image. We have to see how many of those small images can we fit on that big screen. So, the kitchen backsplash is 6 meters long by 1.5 meters high. Remember, we don't like meters. We want to make it centimeters. Everything has to be centimeters because it's easier. Trust. So we're going to change it so that instead of 6 meters, it's 600 centimeters. Instead of 1.5 meters, it's going to be 150 centimeters. You just move that decimal place 2 spots. Okay. So let's draw that. This is 150, 600. Also, obviously, when you do your test, it's a little harder to draw. Like, I know you have the option to. You don't have to do all this drawing stuff I'm doing as long as your work is here. But I will say, suppose your work is wrong, but I see, like, this drawn out. I'm going to be like, oh, look at them. They put in effort. And I'm going to give you points for that because you're actually thinking through it. Just because the numbers are wrong, that doesn't mean, like, you didn't grasp the concept. So, it's always best to show all your work for that complete answer. But you don't have to. I'm also doing it because it's easier for you to see. Okay, we're almost done. Let me stop yapping. So, we got to figure out the same thing as before. Each tile, let's work with the width, right? It's 10 centimeters wide. So 10 into 600, because that's our width. So we're going to do 600 divided by 10. That gives you 60. Okay, so we 60 tiles. Cool, if we take I'm not going to draw all 60 tiles, but we're like, okay, well, there's 60 tiles, 60 tiles. But, again, you can't just do one side. You have to figure out the height, too. Our height is 150. Okay. So, each tile is 10 centimeters tall. Let's see, 150 divided by 10. That means we're going to need 15 tiles up. Okay. So 60 tiles across, 15 tiles high. So there's going to be 60 here. Cool, cool, cool. And there's going to also be 15 vertically. You kind of get what I'm saying? Like, you're kind of building that pattern. It's going to be like each row by each row, but you also need to know, like, there's going to be 15 in the height, 60 in the cross, until you get those square tiles. Okay, so now your backsplash is 60 by 15, and asking how many little tiles will you need for the project? Well, it's 60 each row, right? Each row is 60, and there is 15 up like this. So you're finding the inside of a rectangle. How do we do that? Hopefully you're thinking the area, right? Length times width. So you do 60. Oh my god. Times 15, which gives you 900. I'm going to put that down here. So 900 tiles is what you need. Okay, hopefully that wasn't wildly too long, and you can rewatch it, slow it down, rewatch what you need to do. And yeah, I just really wanted you to get this in a video form so you can ask me questions after or pause it and rewatch things. But let me know if you need any more assistance. We will be taking the test tomorrow and the day after, so study this, have this done. I can take this as a grade. I feel like that'd be an easy little grade for you to have this done. All you have to do is really copy the video. I'm also remembering, I don't know if I filmed this the right way. I think I was supposed to do it horizontally, but we'll figure it out. Okay, bye chat.